Awesome. Hey, everybody. How's it going? Yeah? It's 3 o'clock. It's almost the end of the day. Hello. My name is Irina. I am a software development team lead at Small Media Foundation in London. I just recently moved there from Vancouver, which is also a rainy city, so I moved from a rainy city to a rainy city, and I'm questioning my life decisions. And today, I would like to talk to you about JavaScript and cellular automata, or the hot take on cellular automata, which sounds a little bit confusing, in my opinion. So to kind of, I want to take you on a story. I think that's how we're going to break this down a little bit. So like I mentioned, I'm from Vancouver, and it rains quite a bit in Vancouver. And so it was a rainy day in November last year where when I wanted to go for a hike. And that's what I normally do. I mean, Vancouver is very much like Stockholm, where it's nice and beautiful, and there are mountains, and you just go. But it was pouring so hard that I decided to stop by a library. And our library is like this Battlestar Galactica shooting place that looks like a coliseum, but the main word is Battlestar Galactica. And they had this book sale, and the books were like $2 Canadian, which is like 0.01 American cents, and I don't know how much that is in kroner. But I picked out this copy, this really awesome copy of Hitchhiker's Guide to the Galaxy, and my partner who was with me, he picked out this little black book. And the black book didn't have any names on it. And I was like, oh, what's this? And he pulls it out, and he says, it's Complexity, a guided tour. You should read it. Black book, just like little gold writing on the side. And so I picked it up. I started flipping through pages, and it turned out to be a really interesting combination of all sorts of things that make up complexity. And Melanie Mitchell, who is the author of the book and studies computations and math and kind of writes research papers on that, put that book together and talks about everything from ant colonies, how that makes up a complex system, to entropy, to a bunch of other stuff, including cellular automata. Cellular automata was like maybe 10 pages of the book, but it got me so interested into what it is in general, and what it is a discrete model in computation mathematics, which is, you know, as a developer, you might be interested in that, but you might not be. But I was, so I got coding. And as I got coding, it got super interesting, and it ended up with something like this, which was like, whoa, this is cool. Let's read more about this. It was really cool. I want to be this baby about 90% of the time. Okay, so let's talk about cellular automata. John von Neumann was kind of the first person to talk about automata in the sense that it is today. And you might know him from the paper he wrote on self-reproducing automata, or you might know him from the Manhattan Project, but there have been kind of different things that he was interested in, and it was just fascinating as to how far he's gone from one project he was interested in to another. But he talked about automata, and he talked about two kinds of automata. One being the artificial, the computers, and how that kind of puts together and comes together. And he talked about the natural kind of automata, which is why he was interested in it in the first place, because he thought that this could model what a natural system looks like. And so have other people before him, but he was the first one to kind of talk about it in a self-reproducing manner. So today we're kind of going to be talking about artificial automata. So I kind of want to know more. So let's actually talk about what automata comes and how it comes together and what's it based on. So I kind of broke it down into 4 different parts that it could be basically described as. They were all outlined in von Neumann's paper on self-reproducing automata, but I put them together in like this little check these 4 things when you talk about automata. So first is the fact that the outcome that comes out is dependent on how you describe the elementary parts. And this is essentially the rules that automata would follow. So the result you get in the end is based on how you set out your rules and how your particular parts of the automaton follow them. Number 2 is kind of like this really cool thing where the automaton must have awareness of its parts. So it must be aware of everything that it comes around itself. It's aware of itself and it's aware of everything that's around it. And number 3 is the fact that whatever the operations the automata puts together, it's never directed at themselves. So they never modify themselves. They modify something else. And kind of an interesting aside to this is whatever they produce in general, and that's why it's so fascinating to people, is the fact that the result they produce are very unlike what they actually are on themselves. And number 4, and that's kind of how it ties back to computers and things like that, is that it's decentralized and there's no central management system for these automata. Cool. And that kind of, all these 4 different things that we talked about, or I just mentioned, all come together to the fact that they produce a much more complicated object from less complicated parts. So you have these rules, you follow them, you're decentralized, you're aware, but it's all very simple and it produces a much more complicated object. And when we talk about automata, the number 1 thing we talk about is the Turing machine, because that was like the thing in the 40s. So Turing machine is the automata, and this is an easy way to kind of visualize what an automaton would look like. So you start off with a machine where the automaton produces the action. It produces the action, so it has a specific set of rules it follows based on what it reads or what it's aware of on the tape, which is the product. So it has a specific set of rules, it follows a specific set of rules, and it does its action on the tape that is very different. But it's only aware of like the certain parts around it, so the tape that it reads, which comes up with 2 different constructs, with basically the automata itself, which is the little puncher that punches the holes, and the tape, which just like is infinite in both different directions, comes up to 2 different types of contracts, which is super fascinating, I think, in general. Going back to Melanie Mitchell, she's put together kind of this description, the fact that, again, this kind of reiterates through my talk, the fact that simple components with local information and communication give rise to coordinated global information processing, which is a mouthful already. But basically what it's trying to say is the fact that, again, the simple component that is a hole puncher, with the local information of what it reads directly in front of itself on the tape, it comes up with something that is a Turing machine that everybody kind of knows about. So let's go back to something we talked about, the 4 things I've outlined previously, and number 2 being the awareness. Let's kind of get back into that. So, and let's get back to von Neumann. And von Neumann, when he was talking about his self-reproducing automata, he's built an automaton, and I tried to do a replica of it. And I came up with this, and this definitely looks like the automaton he's put together. So it was basically a bunch of light bulbs that were connected. This is not beer, this is cold brew, I should mention. So these light bulbs were all interconnected by wires, and he's basically said, okay, I'm a light bulb, I'm aware of all the light bulbs around me, so might be in the center, and the 8 around me are my direct neighborhood, and I'm going to be acting based on what these light bulbs have produced, so whether they're on or off, so you're between 2 different states. And he's put it together, and basically he's been able to kind of modify the object based on whether or not and what's in your neighborhood. And so this was kind of like this giant lattice of light bulbs back in the 60s. So this other person comes to mind, and this is somebody, if you've ever been interested in Automata, you've probably heard this name before, is John Conway, or Conway's Game of Life, which is a pretty similar construct. So instead of light bulbs, you end up having kind of, again, two states, and you're also aware of everything around you. And the way I normally explain it is with Koalas and Turtles, just because in computational mathematics, they like to call it dead or alive. I don't like those terms, so I use Koalas and Turtles. But we're in Sweden, and I really like fika time. So I'm going to explain it in terms of cake and coffee. Okay, so you start off as a cup of coffee, and you have all these cakes around you, and your actions are dependent on how many cakes are around you. So if you're a cup of coffee and you have 3 cakes, you become a cake. If you're a cake and there are 2 or 3 cakes around you, you stay a cake. And if there's less than 2 of you, you become a coffee. And these are kind of the basic rules that it follows. So super simple, 2 states. You have this kind of canvas of different cells. But what's fascinating about it is the initial state. So with Conway's Game of Life, everything is dependent on the initial state. And that's why it becomes so fascinating, because based on what is a cake and what is a cup of coffee, you end up with some interesting stuff. There's this one that's a glider, and I think most of you might be familiar with this glider, is that it has the 2 states, and over time, and time just kind of progresses, you're able to change between the 2 different states and produce this kind of really cool, I guess, really cool process, a really cool system that's interesting. And there's a bunch of different ones, and it's all dependent on how you start, obviously. And there's one that's a blaster, and it just like an animation of, I guess, 2 spaceships fighting is what it looks like to me. It might look like something else to you. There's another one that's exactly like a game of life, which if you put it on a large enough canvas, it goes on forever, and basically looks like little cells just spreading out under a microscope. And I think this is why he gave it Game of Life. This is probably not the name. But anyway, so this becomes a 2-dimensional and binary kind of system. So 2-dimensional in the fact that you're aware of everything that's around you being the cell, and binary because you only have the 2 states, the cake and a cup of coffee. Cool. So this next guy comes along and he's like, I want to do it in a 1-dimensional state. I don't want to be worrying about everybody around me. I just want to know the 2 direct neighbors. So Wolfram came in the 80s and put together Computational Theory of Cellular Automata, which is a book that's about this thick. I don't know how many megabytes that is in EPUB, but an actual book is pretty thick, and he's come up with 256 permutations of different rules that could kind of get these automata to follow. And I kind of built out the rule number 110. So again, it's a 1-dimensional array, it's binary. So you start off as a cup of coffee, and you only care about the 2 cakes around you, so it's nice. You don't have to worry about all the other neighborhoods. And so if we take a look at it a little bit more, it's basically a 1-dimensional lattice of your 2 states. It could be anything between 2 to 50 to 60. And as time progresses, what happens is that you are going to be looking at your neighbors and basing your next generation action based on what your neighbors are. So you're going to look to the right, and then you're going to see what your sibling is like. And then you're going to look to the left and figure out what your sibling is. And then you're going to follow the particular rule based on what your right and left sibling is. So I used parent cell when I was kind of building this out in basic JavaScript just to get my feet rolling. I just built this out in the DOM because why not? It's fun. And I looked at the parent cell to be able to figure out what I was before as a cell. So based on what I am on the right and on the left, I can then toggle kind of the class, the 2 states between active and inactive. And that's what kind of gets it to this particular pattern. And what's fascinating about this one is that it's known to be Turing Complete, this particular rule. So Wolfram's put together 256 of them, but this particular one is meant to be Turing Complete, and it's different based on every time you set a random state, which is super fascinating, but you still have kind of like the same pattern going down as you change the random initial state. And so I guess when I kind of read this, I was like, oh, Turing Complete, what is Turing Complete? Because I've never encountered that before. So I decided to search on the internet, and I found a definition where a computational system that can compute every Turing computable function is called Turing Complete. Alternatives such as a system that can simulate a universal Turing machine, which is pretty cool. So it can simulate a Turing machine based on like these super simple rules, but it's so complicated that we're not able to, that it's considered Turing Complete. And so based on kind of like this pattern that we were able to put together with Rule 110, or Wolfram was able to kind of generate with Rule 110, it could be noticed that certain patterns end up dominating in that particular setup. And so then a pattern becomes a set of configurations that share a common spatial structure, which in that case is a bunch of triangles, but they do share that spatial structure between them. And then what people put together and kind of discovered is the fact that there is an extreme diversity of this behavior of these triangles, where a system will organize itself into these particular patterns, and it organizes itself into patterns, which has been super interesting to me. Like, based on these rules, how do you end up like in such a complicated pattern? And so I've then been reading a bunch of more literature on this automata concept, and I came across something that's called an it from bit theory, which I find incredibly fascinating. And it basically says that everything derives from binary yes or no answers in terms of kind of physical states in the world, and it symbolizes the idea that every item of the physical world has a bottom at the bottom, and then material source and explanation that we call reality arises in the last analysis from the posing yes or no questions and the registering of equipment evoked responses, which was kind of this entire theory came from John Archibald Wheeler. And what's incredibly fascinating is the fact that these spatial temporal responses are all based on this binary yes or no, or cake and a cup of coffee responses. And so again, these spatial temporal behaviors are ending up being quite complex, which leads us to complex systems. And what people have reiterated over and over again is the fact that automata are essentially complex. And then I was like, oh, what's a complex? What's complexity? What is it even? I mean, we work on different programs during our day jobs, and sometimes we call them complex, and sometimes we say, oh, this is complexity. So I felt like this was actually related to what I do during the day job. So I Googled complexity, and this is what came about on the internet. The state, a quality of being intricate or complicated, which is what is complicated, I don't know. Then I went on Wikipedia, and they were saying complexity is generally used to characterize something with many parts, where those parts interact with each other in multiple ways, culminating in higher order of emergence greater than the sum of its parts. And that was also kind of confusing, but also the sum of its parts, okay, yeah, that kind of makes sense. So something that's a lot more complex than one we started off with, or a lot more complex than the rules that in the case of automata, the rules that the automata follows. And then there's this set of really interesting talks, or I guess university lectures, provided by Seth Lloyd, and he tried to describe complexity by answering 3 questions. How hard is it to describe the particular system? How hard is it to create the system? And what is its degree of organization? And kind of answering those questions, you're able to derive to the answer of whether or not something is complex. which is interesting. And then I went back to some of the Melanie Mitchell's work, who initially started this entire search for automata and complexity. And she's put together a couple of things that I thought were quite relevant, or I thought explained a lot to me. And one of them was saying that the average amount of surprise, or the average information content, is what makes a system complex. And average information content was a little bit confusing, but then she goes on and says, algorithmic information content, or average algorithmic information content, is the size of the shortest program to generate a complete description of what you've put together. So in the sense of automata, it's probably going to be, if you're just having like two lines, two different binary state lines, it's probably pretty easy to generate a program that will be able to reproduce the same thing. But in case of, for example, Rule 110, it might be a lot more complicated. So the average algorithmic information content is a lot more easier for me, I guess, to grasp in general, because it's just kind of, is this number higher than this number, in a sense. So that brings me to genetic algorithms and cellular automata. So we kind of went over complexity. We've kind of went over cellular automata as the initial concept of such. And the reason why people have been trying to implement kind of these genetic algorithms is because, in a sense, the one-dimensional binary automata is a very simple representation of a particular system. And it's much easier to get it to manipulate to do certain aspects of whatever it is you want to do than starting off, for example, with a two-dimensional binary automata like Conway's Game of Life. And then you're able to reproduce these particular systems and kind of able to mimic some biological, for example, structures. So because these such simple systems produce complicated results, people decided to kind of look into it. So let's go back to Neumann. When he's put together his paper, or I guess the person he's worked with put together the paper from his lectures on self-reproducing automata, he's talked about kind of what this ideal automata would look like. And it started off with basically you, the automata, being able to access different parts of your system. So you might have various things you might need as you work, as you reproduce, as you create. You have specific rules you follow, but you kind of just want to make them on your own. So you have to have all this availability to different parts as the automata. And when he's said it and he's put it together, when we kind of interpreted it, it basically turned out to be computers. But the reproduction kind of came from that, and the fact that as an automata, I want to be able to access everything that I need to access to be able to reproduce. But again, when he's put it together, it was a two-dimensional binary automata. And I've been interested in the one-dimensional one because it's a simpler representation of the system that I'm able to then generate something else. And with a single-dimensional automata, people have been putting together some pretty interesting things that could amount to something a lot greater. And so some of the things that have been put together is kind of these three concepts, and there's a lot more of them, but the three that I liked have been the density classification, the synchronization, generating random numbers. People have been using it for image processing. People have been using it for sound processing, which is pretty interesting too. So I wanted to take a look at density classification. And density classification is pretty interesting because you're basically trying to get your automata to vote. And what I mean by that is you start off with a random lattice, and you say, I have a bunch of, again, we're starting off with the same thing. I have a lattice of different states. And what I want at the end, after I've gone through many generations and many iterations, I want to have the best automata that will get the opposite of what the average is for a particular lattice. So this one is actually average, so equal amounts of cake and coffee. But if I were to start off with extra cake, I want to end up with more coffee at the end. So this is like getting your population to vote for somebody other than what they start off with, wanting to vote, I suppose. So what happens is that you start off with this random lattice, and each one of them has a different set of rules it follows. So it's not the same set of rules across the entire lattice. It's a different set of rules. And you don't know, in your initial generation, you don't know how each one of them is going to perform. And what you want to find out is which one's going to be the fittest, who is like the best runner, the best weightlifter. And as time goes on, you are then able to average out and say, okay, so given this particular cell, over the 150 years in one generation, it was able to get from, consistently, it was able to get to a cup of coffee at the end, as when it started off with a cake. Which basically, like I've mentioned before, is this concept of, can you get your neighbors to work for somebody else? And this lattice here, if I were to run it over 5 years in one generation, it obviously wasn't able to, so it's not performing very well. But if I had a cup of coffee and then I ended up with a cake at the end, which I didn't end up even here, then yes, that's a win. And if that happens more and more often, then we're able to say, yes, these cells are performing well. So Melanie Mitchell initially wrote this paper on density classification, which is where I got the inspiration for this, or the interest to this. And she's ran it over several generations, 150 generations kind of thing. And what then happened is with generation 0, you start off with majority black cells, and you still end up with majority black cells at the end, so clearly none of your automata performed. But you can then say, okay, so if in generation 8, for example, I have more white cells, and in the end I actually start ending up with more white cells, then I've done a lot better. And over time, you're able to then get more and more, or you get better and better based on what your algorithm picks out. And it could pick out 20 best performers in the particular set of cells, or 60 best performers, or 10 best performers, and see where it gets you to. So this is about automata and genetic algorithms. I think it's been a really interesting kind of set of research for me. I've enjoyed putting it together. I've enjoyed playing around with different things that I've read and different things I've been putting together. And I think it's a super interesting topic to go back to. And I mean, some of you might have studied this in school. I personally didn't. But even though it's something that, for example, you can get during those interviews with company X, putting this kind of thing, and then you get turned off from it because, I mean, you had to do it under pressure. It's actually been quite fun. And I hope you also get to explore and play around with some of the concepts that put our computers together and put our programming together. I've compiled a list of some of the better papers / books I read on this subject, and I'm going to publish the slides online. Come say hi to me on Twitter. I'm most attainable there. I will post these slides in a second on Twitter once I'm off the stage. And I might also, there's a chance there might be a YouTube video of cellular automata in the near future. Might. If such were to happen, it would appear on my Twitter, maybe. YouTube video, maybe. So thanks so much for having me. Thanks.